Hello everyone and welcome back. Now that Lee's got all of the 2D and 3D noise algorithms implemented, it's time to look at a little bit of optimization, right Lee?
Yep, because this is something that we want to run as fast as we possibly can. So before we can optimize, though, are you taking my mouse again?
Yes.
You're supposed to say, no, it must be a problem on your side.
That's what I said. What'd you hear?
Yeah. All right, but before we make any changes, it'd be kind of nice to know what we're running at to see if our changes actually have any difference or make any difference. So we'll run through this real quick and try a run with each of our noises. So 25 milliseconds for our value. Now, I've already gone through and made this really, really high-tech before and after graph for each one of our noises.
Yeah.
Actually, all of our noises are going to be in milliseconds, so I'll just put our numbers.
Just a given, yeah.
Yeah, so because our algorithms are so awesome that way. They run so fast now. All right, so 25 milliseconds for value.
We'll go with 38.
Okay.
For Perlin.
So 38 for Perlin. Come on, I know thought I clicked. Guess not. All right, and our simplex. And about 32.
Yeah.
All right, let's start looking at our 3D implementations. First up is value. And 38.
Over one. There you go.
I'll get there eventually. Figure if I click enough buttons, it'll do what I want it to do. All right, 57.
Yeah.
And this one.
And 38.
Okay. All right, now we've got our befores. Time to do some optimization. So let's start off with value noise. So if we jump over to our value noise and we look at what we've got, we've already optimized this an awful lot. The point now that I feel comfortable getting rid of all of the smooth noise stuff, which means all this code is no longer used. So we'll clean that up. Also means all of this is no longer needed. And that should mean that I don't need these two methods. All right, so that gets rid of all those. Now, what can we do to optimize this? Well, we've already done the greatest bulk by getting rid of all those smooth functions in the hash 2D and 3D. But we're still calling this method here, this floor method. And that floor method is inside of the noise. Now, one of the reasons that I wanted to implement our own floor was this is a little bit faster than the math functions floor. But it also gives us an understanding of how floor works.
Don't say that since it's not
It's not 100% implemented for
Okay.
the mathematical function. We understand. We explained
Let's
that in
just
an
call it
earlier
Lee's
video.
floor, okay?
Yeah, it's Lee's floor,
That's
but
better.
it's also fast. And the reason we implemented it this way is so when we got to the optimization part, I could replace the method calls with the internals of that method inline. Now, calling a method isn't really expensive,
I
but
thought if it was only one line in a method like that, that
the compiler
the
should
compiler is
inline.
going to inline it. But I mean, if we see a performance boost out of this, then it wasn't being inlined. I've not done a great deal of study into the CLR, so
And then we're also talking about
into the
mono
compiler.
and unity and stuff as well, and what it does.
Yeah, that's true. So
So what I'm going to do is get rid of all of these floors, and we're going to inline it. So that takes care of both of our 2D and our 3D floors. And if I build this out, no errors. Well, I
yeah,
actually,
go to your game manager and make sure we're
yeah, I
using.
need to change that there. All right, so let's start off with 2D. So now we can run it. Here's our 2D, 23.
23.
So,
Definitely made some sort of difference.
yep. So, yeah, I'll bring up calc real quick. Let's see it, so I'll type it. All right, so
Please don't tell me you're going to take 25 minus 23.
what?
Oh no, good. You're going to get the percentage. Never mind.
Thank you.
I thought you was about to say, as you can see, there is a 2 millisecond difference.
That's cold. That's really, really bad. I just don't know what to say at that
Well,
point.
that's just how bad it startled me. I thought that's what you were going to do. Wow.
Oh man, yeah. As you can see, we're looking at higher order double derivatives of math functions. Okay, now 23 minus 2. Let me get the calculator. Or 23 minus or 5.
25 minus 23. You can
See,
do
look,
it,
I'm
Lee.
so flustered now. Okay, so just by removing those inlines on the 2D, we got an 8% speed improvement. I'd say that was a worthwhile change. So let's look at our 3D. And so 35.
35, yeah. Where are you going? Where are you going?
What?
3D, down.
I was just putting the spaces in.
Oh, yeah, nice recovery.
Yeah, that's what I was doing. See? Look at that. So 35. See, I'm going to do them for all of them so I don't have to come back and worry about it later. Then I'm going to go over here and add some more. And then hopefully I didn't close the calculator, but I probably did because I was being distracted. All right. So as you can see, 38 minus 35 comes up with 3 milliseconds. So if we divide that by 38, we get just under 8. So I'm going to round that up to 8%. That's close enough. I'm going to move that off to the side because I don't want to have to go
Just
open
say
it.
7.8%.
Okay, fine. 7.8%. Actually, 7.9 because that rounds to 7.9 if we're going to do it that way. So 7.9% speed improvement. And that was just by inlining 2 method calls inside of 2D and 3 method calls inside of 3D. Now, with most stuff, if you're only calling it occasionally, it's no big deal. We're literally calling this particular number hundreds of thousands to millions of times each time we generate the texture, depending on how big the texture is. So every little bit of performance that we can shave off per cycle is going to add up for us, which is why we're doing this. If I jump back over into code, comment this out, let's go look at 2D Perlin next. So we've got the same thing here with our floors for X and our floors for Z, which we've already done with value noise, which apparently has disappeared. All right, so because it's the same thing, I'm going to copy them from value noise to save us some time. Paste it here. Remove it from our 2D because we don't need Z. Paste it here. So that takes care of our 2D and 3D Perlin, but we're not done. We also have this fade that is being called twice in 2D and 3 times inside of our 3D. So let's go take care of that as well. Fade is housed inside of here, and it's this, I think they call it a 5th order quadratic equation, but I'm not positive on that. So, and Perlin noise. So what I'm going to do here is paste this in, and everywhere where there's T, I'm going to replace that with X. And then for Y, same thing, but instead of X, we use Y. Now, we can take this technique and go crazy with it, meaning we could inline our dot product calculations. I'm not going to go that far. But, if you're venturesome and you want to go ahead and inline the dot products, go for it. And go ahead and post the results that you get up online in one of the forums. Let me know how it turned out. And for that matter, all of the lerps as well could be inlined.
Mm-hmm.
But this is just the fastest way to show some performance increase without spending the next hour taking every dot product and every lerp and inlining it. So that will take care of our fades and our floors. So if I go back to noise, fade should be obsolete, so we can get rid of it. We're already set up for our Perlin 2D. So our Perlin 2D is 36 seconds now, or 36 milliseconds.
Mm-hmm.
So we're down from 38 to 36, which is going to be, what, about 6.97. So that's 3. See, maybe I need to subtract. So 3 divided by 38.
3.
Yeah.
Oh, wow. You're looking
Oh,
at...
no, yeah. I see what I did. Never mind. I got
It's like you're
all
doing
messed up.
some math I don't know about.
Yeah. I'm still flustered with that other one. So 0.53. So that works out to be 5.3. So 5.3%. And then let's jump back over to the game manager and look at 3D. And 52. Yeah, it's staying at 52 more than 53. So 52. So that will be 5 divided by 57. So 8.8. And back over and set up for simplex. So simplex noise here. All right, now our floors are going to be slightly different than we had before. So because we've got this x plus s and the y plus s. Paste this in. Take that. All right.
Do you want to leave that -1 at the end? Oh, yeah. Da, 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 da.
Doesn't matter. Whoa. What was that? Control V. There we go. All right. So change the x's to a y. We can always use our standby. It's getting late. It's been a long day. And do the same thing down here with these two. Change up this to BZ instead of Y. So that should take care of those. And again, same thing here. If you wanted to go through and inline the dot products, you could for a little bit more performance. All right, let's go see what we got.
Well, even for a little bit of performance there, you could have just done a variable, since they're just value types, and
So we're down to
31.
31.
So that you didn't have to repeat the operations over and over.
This is true.
But it's good. 31. Notepad.
Yep. So 2D. Not much of a performance increase on that one, but still a little bit. So 3.1. But at least I think they're getting the hint. There's a lot of little tricks that you can do. So anything that you can inline or simplify the equation so you're not repeating over and over again. Don't do any type of mathematical operation that you can simplify down into a constant and then just use the constant instead of always calculating out the value. And back here. All right. And
37 more. So again, just one.
yep. So it just goes to show that the simplex is pretty optimized.
Mm-hmm. But now you do have value 3D faster than
Yep. So with optimization, you can make value faster than all the others, but it still looks terrible when animated compared to the other ones.
mm-hmm.
So what is that? 2.6. So it does bring up a good point that while value noise is definitely faster, if you want something that's going to be an animated texture, value noise probably isn't going to be your go-to noise. You'd probably just take the little bit of performance hit and go with the simplex. But if you need a lot of noise and you know it's going to be static, we've already shown that the value output of the value noise on a static 2D value compared to a static simplex
Mm-hmm.
are very similar. So if you look at the difference between the numbers on our optimized for our 2D, 23 milliseconds as opposed to 31 milliseconds for simplex. So if your noise is going to be static, you'd probably be best off to go with the value noise.
Mm-hmm.
But if you need something that's going to be animated, say a cloud texture or any the motion of characters or the surface of water, then simplex would probably be the noise that you want to go to. That's one of the reasons we've implemented multiple types of noise, and we're going to wrap all these up into a library of calls that you can go. So depending on what you're doing, if you need simplex, you'll have simplex available. If you need value, you'll have value available. And if for some reason you need Perlin, that'll be available to you as well.
Awesome.
So, plus the really great educational value you get out of learning how noises work.
That's true.
All right, so that will take care of that. So this is our optimization. Now, there is more optimization that you can do. And if you wanted to take a real close look at it, like I said, unrolling the lerps, unrolling the dot products, as Jason had mentioned, going in and looking for duplicated mathematical operations and simplifying them anywhere that you can find them. So you're not doing the x plus s and the y plus s multiple times. So if you want to have at it and have a little game with it, see who can come up with the fastest implementations of noise. Go for it. I'd love to see the results that you've got. But
Of course, that's also hardware dependent as well.
this is true too.
Reminder.
Yeah, but if they think that they've got something really good, go ahead and send me the DLL. And we'll run it. We'll all run it against Jason's machine and see how well we get. And I mean, it is noise, and the fastest noise we can make work that looks good will help everybody in the end. But that was everything that I wanted to show as far as the theory behind the different noises, getting them implemented in 2D and 3D, and optimizing them. In the next several videos, actually, we're going to have some fun with them, because while we can go in and generate our noises, if you look at our game manager, there's a bit of work that we have to do inside of the update noise to get a noise texture out of it. I don't want to force our coders to have to use this. I want to take all this information, wrap it up so all a coder has to do is go, give me a value at this location of this type of noise. Or even better, instead of doing this loop, be able to go, I need 6 octaves of noise starting at this position in a texture or a set of data that is, say, 128 by 128, and just give me back that array of values. And then I'll do what I need with those values.
Mm-hmm.
So in the next set of videos, we're going to put that in place, as well as adding controls for doing things like adjusting the frequency, the number of octaves, the persistence, the lacunarity, the gain of the textures that we get in. And over the next few videos, we're going to get a nice little framework together that I'll be able to put together a demo where we can interactively change our noises on the fly so you can see what those settings are doing. So you can play with them and use this application going, you know, I need a noise, but let me play with these settings, and you can get a ballpark idea of what that noise is going to look like without having to, you know, go in here, dial in a couple of numbers, build out, run your game, go, no, that's not what I need, go back to code and change it and repeat that over and over again. We'll actually set up some sliders in there as well. So you can bring up a little menu, and it'll allow you to adjust the sliders. It'll allow you to select your value noise, your simplex noise, your Perlin noise on the fly. There'll be no more of this back and forth. We'll have that all inside of a little demo framework for us to play with noise.
Awesome.
And it just really looks cool. I mean, you can dial in some settings, and I'll just put it on my side monitor and let it run while I'm doing other things, because it looks like the one instance I was showing you kind of looked like a little lava lamp.
Mm-hmm.
It was awesome. So I just let it run for hours on end.
Awesome. All right. Well, let's go ahead and wrap this quick optimization video up and move on into that good stuff. So with that, that is going to wrap up this video. Thanks a lot, everyone.